Hi, thanks for joining me. I have developed a summary chart of what I've been talking about with free energy and enthalpy and entropy, and I want to go over it with you. You may have to pause to fill it in because there is a lot of writing here, and I don't want to spend too much time going over this. But it will be well worth it if you actually write it in as opposed to take a screen capture. Screen captures just aren't active enough to improve your learning. So the terms we've talked about so far in thermodynamics is enthalpy. Enthalpy is about heat transfer at constant pressure. So you would say heat is Q at constant pressure. Now, what's key here is that the units are typically given in kilojoules, maybe kilojoules per mole or kilojoules per mole of the reaction occurring. I have a video on a mole of reaction if you are interested in how that is applied. Its signs, if it's positive, it's endothermic, and that's not favorable. That doesn't mean a reaction would not be overall thermodynamically favorable. It just means we have an energy barrier that has to be overcome for that to occur. When it's exothermic, heat is released to the surroundings, and that's a favorable heat exchange. Entropy. Entropy can be a pretty abstract concept, so I like to give a variety of ways to think about it. It's the arrangement, so the more you can arrange molecules and rearrange molecules, the more entropy the system would have. We would call those arrangements, each individual arrangement, a microstate. We can talk about freedom or degrees of freedom and motion. You can talk about dispersal of matter, or commonly about disorder. Increased disorder is increased entropy. Now, what's important for you to note here especially is that it is typical, since it is a smaller magnitude, to report it in moles. It can be, in joules. It can be joules per mole Kelvin. I really should have put in here, if it was a reaction, it could be joules per Kelvin. I'm going to put that first, mole of reaction. Okay, but the key is it's in joules. So if we're going to be working with these, we're going to have to be careful to make sure we're dealing with the same units. So you're going to have to convert one or the other. A decrease is not favorable, and that would be a delta S, not negative. An increase, that's why I like freedom a lot, because an increase in freedom is very positive, and that's favorable. Okay, if I combine those two, we've seen that formula in one of my earlier videos. Delta G naught is equal to delta H naught minus T delta S naught. That's the maximum amount of non-pressure volume work available in a closed system. The key is it's a balance between our entropy and enthalpy that is going to be our key indicator for the favorability of a process. Much like enthalpy, it's typically given in kilojoules, maybe per mole or mole of reaction. But if we're going to apply it to this formula, they either have to be all joules or all kilojoules. So be very, very careful what you're using. Joule would be the SI unit, so some of you may want to convert to joules. Because there will be a context later on that you will have to make sure that your free energy is in joules, not kilojoules. But the key there is make sure they're all the same. If it's positive, it's unfavorable. Biochemistry especially calls that endergonic, and that is not thermodynamically favorable. Whoops, I have a typo here. If it's negative, it is exergonic, and that is what is thermodynamically favorable situation. Well, what does that mean? Well, let's link it to our equilibrium constant. That's our law of mass action when rate forward equals rate reverse. So that point at which the rate of forming products is equal to the rate of reforming reactants. It's considered unitless for a reason that's beyond the scope of our conversation here. But this gets the heart of thermodynamically favorable. Thermodynamically favorable means to proceed to make buckets of products under the conditions given. Okay, not thermodynamically favorable would be reactant favored. So if it's reactant favored, remember K loosely speaking is products over reactants. If the denominator is bigger, K will be much less than 1. Won't be negative because negative molarities are illogical, but it'll have often a very, very negative power, like 1 times 10 to the minus 20th. Okay, it can be a very negative number. If it's thermodynamically favorable, it's product favorable, so that means my numerator is much bigger than my denominator overall, and so K would be greater than 1. Wow, that's a lot, but that's a summary of a lot of concepts that have been covered hopefully in your class or in my previous videos. So slow that down, pause it, make sure you wrap your mind around these because these are very, very important conceptual ideas that you need to understand because the mathematics is great, but if you don't have that underlying understanding of the concepts of chemistry, the mathematics are just an algorithmic routine. So I hope you can understand this so the mathematics makes more sense. So thanks for joining me. I appreciate your time.